Okay, in this video I wanted to explore some force fields a little bit more. I want to start by taking a look at a gravitational force field. So I'm going to let big M represent the mass of the sun. I'm going to let little m represent the mass of a planet. Could be the Earth, could be Mars, whatever, but I'm going to pick one planet and we're going to work with that right now. Now, the way gravity works, the sun and the planet actually both exert the exact same force on each other. Okay. However, because the sun is so much more massive than any of the planets are, the effect of that force is seen much more in how the planet reacts to that than in how the sun does. If you sort of imagine it, if you went up to a person and pushed them, okay, if you did that to a little tiny child, and I am not encouraging you to go out and push little tiny children, that would be wrong. But you can imagine that the force it would take to knock over a little tiny child, again, do not do this at home, okay, that if you applied that same force to a big honking adult, the adult might say, "Why are you touching me?" but would not fall over, okay. So that's just that the bigger object might have the same force applied to it, but isn't going to react as strongly as the smaller object. Okay. So for that reason, even though I know both the sun and the planet are exerting a force on each other, I'm going to think of this as just the force that the sun is exerting on the planet. Okay. And I'm going to set up a coordinate system where I'm going to put the sun at the origin. So I'm going to put the big mass here at the origin. The planet, that has a little mass of m, is going to be somewhere out in space, and I'm going to use r as my radius vector that points from the sun to the planet. Okay. And I want to try to figure out what the force of gravity is on this. Okay. Now to do that, I'm going to need two things. I'm going to need the magnitude, and I'm going to need the direction. And I can specify the direction with a unit vector in the direction of the force. Okay. So I'm going to be writing out my force as F of R. If I can get these two pieces, I'm going to be in good shape. Okay. Now let's start with the direction. I know that gravity is an attractive force. So the sun is sort of saying, "Come hither, come to me." So the direction of the force is going to be exactly the opposite of the direction of r. Now, r is not necessarily a unit vector, so the unit vector that would point in the correct direction then will be the opposite of r hat, which is just the opposite of r normalized, scaled by the reciprocal of its magnitude. Okay. Now, the magnitude of the force, this we're going to get from Newton. And some of you might be familiar with it, and some of you might not. It's going to be gmm over the magnitude of r squared. M and m are the masses of the sun and the planet, respectively. G is a gravitational constant. Gravitational constant. Those of you in physics might actually know what the numeric value of that is. I never remember it. I just write G. Okay. But we get the product of the masses times this constant divided by the magnitude of r squared. Okay. So we're saying essentially that the force is inversely proportional, where I've got this constant. These things aren't going to be changing. A different planet might have a different mass, but that's a different problem. I'm talking about one planet. These guys are all constants. So this is inversely proportional to the distance between the two objects. And whenever I have a force where the magnitude of the force is inversely proportional to the distance between things, we call that an inverse square field. Okay. All right. Excellent. So this is what we get. If I put the pieces together then, I'm just going to take the unit vector that points in the right direction, and I'm going to scale it by this magnitude. But usually I'll probably rewrite this. I'm going to just bump that negative sign to the front and associate it with that constant on top. And then that actually gives me 3 factors of the magnitude of r on the bottom. So I end up just getting a multiple of r. With gravity, since it's an attractive force, it's a negative multiple of r because it points in the opposite direction of r. Very interesting, I get the magnitude of r cubed on the bottom, even though we said this was an inverse square field. And this really indicates why. The square of the magnitude shows up in the denominator of the scalar, which is giving me the magnitude of the force. But then there's a third factor of r because what I'm scaling is the unit vector that points, in this case, in the opposite direction of r. Sometimes we'll have a repulsive force that'll point in the same direction as r. So, this is our first example of what we call an inverse square field. And in general, we can always write an inverse square field this way. If I have an inverse square field, it's going to be f of r is the magnitude times a unit vector. The magnitude is going to be some constant divided by the magnitude of r squared. I'm going to let that constant absorb the sign of the unit vector that points in the right direction. So here I'm just going to put the unit vector in the direction of r. If c is a positive constant, this is the direction in which the force acts. If c is a negative constant, this is pointing in the opposite direction from the force. And then we can simplify this to c over the magnitude of r cubed times r. Sometimes tricky to remember that there are 3 factors of r, but if we remember that the third one comes from the fact that we're scaling the unit vector, then we can remember that. Now this is a very convenient way of writing this because I'm writing it with just some constant, and that's going to vary depending on the circumstances, some constant, and then I can write everything else in terms of this position vector r. Now there will be times though when we're going to want to write this in terms of its components. So I might want to write, instead of f of r, f of xy, if I've got an inverse square field in 2 space. Of course, in 3 space, it would just be f of xyz. Okay. I'm going to just write it out in 2 space. Notice, if that's the case, r, remember, is just my position vector. So r is just the vector xy. So this would become c over the magnitude of r is the square root of x squared plus y squared. That gets cubed, and then we're scaling xy. Now, I can go ahead and do the scalar multiplication. That's going to make the components of my vector cx over, I think I'm just going to write that as x squared plus y squared to the 3/2, and then cy over x squared plus y squared to the 3/2. Important to know both this characterization and this characterization of an inverse square field. This is very nice and concise. This is what we'll need if I need to be taking the partial derivatives of my component functions. Because I know how to take partial derivatives with respect to x and y and in 3 space z. Don't really know how to take derivatives with respect to r, the position vector. So when we need to work with things at the component level, we want to be able to convert it to write it this way. And of course, if it's an inverse square field in 3 space, my r vector is just x, y, z. So there would be a z here, and there would be a plus z squared in the formula for calculating the magnitude of that vector. All right. Now, another important example of an inverse square field is the force between charged particles. I'm going to just draw this one in 2 space, although we could certainly do this in 3 space as well. I'm going to let Q represent a big charge. And I'm going to let little q represent a little charge. Now, just like with gravity, two charged particles are going to exert the same force on each other. I am, however, going to think of this just as this is exerting a force on this, because the little charge is going to react more to that force. So the effect of the force will be much more visible if I look at what the little charge is doing. So just like I did with gravity, I'm going to put the big charge at the origin so that the little charge is somewhere out here in space, and then r is the position vector that points from the origin to the location of that charged particle. Okay. And I want to find f of r. Okay. And Coulomb's law tells me that the magnitude of that force, it is going to be an inverse square field. It's going to be epsilon q over the magnitude of r squared, where epsilon is a constant, and then this is the product of the charges. Okay. Now, those of you in physics, the constant sometimes gets written different ways. Sometimes it gets written in terms of an epsilon naught, sometimes in terms of a k. I'm not sure exactly what notation the physicists are using, so we might be calling the constants by slightly different names, but it's just a constant multiple of the product of the charges divided by the magnitude of the distance between those charges squared. Okay. Okay, so, oh, and I'm sorry, I should have, for Coulomb's law, put an absolute value around that, because of course the magnitude of a force has to be positive, and the charges are allowed to be either positive or negative. But what's kind of nice is now if I put this together, I'm going to actually take that signed magnitude and use it to scale the unit vector that points from Q to Q, and the sign here gives me the correct sign to go with the vector that would point in the correct direction. I know that two particles that have the same sign repel each other. So if these have the same sign, this is going to be a positive number. So the force is acting in the direction of r. That would be away from Q. That's a repulsive force. On the other hand, if the charges have opposite sign, that's going to be an attractive force. So that would make this negative. If I bump that negative sign over here, the unit vector that points in the correct direction would be pointing towards the big charge at the origin. Okay. So this becomes epsilon q over the magnitude of r cubed times r. I am not concerned that you remember that epsilon is the name of the constant that we're using in this particular example. What I want you to know is the general formula for an inverse square field, which is the one I had up a moment ago. That's going to be c over the magnitude of r cubed times r, some constant. I would give you any constants that you need, or I might give you a generic one where you just say, oh, there's a constant on the top. Okay, and then the constant, the magnitude of the constant, contributes to the magnitude of the force, and the sign of the constant is going to determine whether it's an attractive or a repulsive force. Okay, excellent. This video has been going for a while, so I have a little bit more to say about these force fields, but I think we'll start that in the next video.